This is a tutorial video that goes over GLMsingle. The goal is to explain the figures and how to interpret the figures and to assess different types of data sets. This assumes familiarity with the tool and the documentation, but again, the primary goal is to talk through the figure outputs. What I have here are a diverse set of data sets. There's 8 of them here, and I've already run GLMsingle on each of them. And just to give you a little bit of orientation, I'm just using the vanilla call to GLMsingle. I start with appropriately prepared design matrices. For example, 300 TRs, 583 conditions, 12 runs. And in this example, we have a data set. It's deliberately small just to make the examples more tractable. We have XYZ. There's only one slice in this preparation, and so XYZ by time, where this is the number of TRs effectively. Right, so we have data, design, and we have stimulus duration is 3 seconds, TR is 1 second. So that's the basic format for all of these examples, and I've already run the vanilla, very default call to GLMsingle, as you can see here. This is the MATLAB version, where I just pass these appropriately prepared variables to GLM estimate single trial in a folder for the outputs. Okay, so let me dig a little bit into the figures and the outputs that we get. Perhaps first off, we'll go into this folder, and there's a bunch of figures, and the main outputs of the tool are these 4 files here. Again, I sort of assume familiarity with the meaning of these files, but let's just take a quick look. Actually, let's not run that. Let's save it within a variable here, and you can see various outputs in this file, type A, which are documented on the function documentation at the bottom, as you can see here. So I won't read this, but just point you to its existence. This is on the Read the Docs website, and you can also look at it on the actual code, the GLM estimate single trial.m file. Okay, so that's just the type A model. We can also look at the other models, so let's just jump to this one. So I load that in, and it has different fields reflecting a different model and some more sophisticated processing, so on and so forth. Okay, but primarily we're concerned with understanding the figures. So let's start with example 1, and we'll sort of compare what we see across these different data sets. Let's just start with the first alphabetical one, frac value. So this shows you, for just this data set, these are 3 slices taken from some fMRI experiment, and we're visualizing the fractional regularization level. It's a number between 0 and 1. 1 means no regularization, 0 means heavy regularization. Actually, the default in GLMsingle is to, if you look at the fracs input option, it's actually not 0, which would mean infinite regularization. It starts at 0.05. Anyway, so the range by default is 0.05, increments of 0.05 to 1, and here we're looking at that in terms of a copper color map. This basically tells us where good voxels are. In the ideal case, you would not need any regularization, and it does look like that's what's happening in these regions. I guess it might be useful to open these up simultaneously, and you can kind of see by eye that these locations sort of make sense, given this was an auditory experiment. So frac value just gives you a sort of diagnostics of where it thinks voxels containing repeatable signals are. We also have href index. This is a little difficult to look at because it is the selected index from, by default, 1 through 20 of the href library, and we're just visualizing that using a jet color map. But it's very hard to see often where the signals are because most voxels don't have any signal, and it still nonetheless picks an href. So let's just look at a few of these, and then we'll also compare across data sets. Noise pool is probably not that important. It's showing you what it used as to derive the GLM denoise nuisance regressors from. White means it was selected. There's a step that basically excludes voxels with signals as determined by a quick on-off fit. So it's basically brain voxels excluding relatively high voxels here. And while I'm at it, this is sort of an interim model that it fits this very simple on-off model. So it collapses all the conditions into one predictor and just fits a first pass GLM just to try to understand where signals might be. And as you can see, it's brighter is better. This is a hot color map with a square root hot color map, just to accentuate the low intensities. So let's kind of compare so far these figures on different data sets. So here's an example of a data set with very good signals. Let me open up a couple of these in one window, and then I'll do the same for this first data set. And let me zoom this a bit. Okay, so if we compare these data sets, they actually have drastically different SNR qualities. And this is a function of many things: the field strength, the spatial resolution, the compliance of your subject, the efficacy of the design, whether it's short events, long events, blocks. So many of these differences are expected, but the goal here is just to try to understand what we're seeing. So as you can see in this data set on the right, there's extensive signal in the back of the brain. Again, these are the fractional values. A lot are essentially pure. I assume these are ones, but it does grow, it does decrease a little bit, meaning that a little bit of ridge regression regularization was used for some of the voxels on the outskirts. Now, if you compare the HRF index, you can actually tell now that there is stable structure. The HRF index, there was no spatial constraint put on it, hence any kind of structure or low frequency patterns we can see here it indicates strongly that there is a good signal. Here's the mean volume, just for reference, which is the mean fMRI volume across all time points. And here's that quick and dirty on-off R squared. So if you compare these two data sets, vastly different number of voxels, and this actually achieves very high R squareds given the yellow, which is not to say there's anything wrong necessarily with this first example. It's just weaker signals. Let's look at maybe one more example. Let's go to example 8 for these quantities. So again, I'll zoom in. These example data sets are, these are just two, in this case, 2 slices. There are many more slices in the full data set. Okay, so in this example, we have the usual frac value. Notice heavier regularizations being used. We rarely get this very bright color, which presumably is like close to 1, and often we get fractions closer to 0. The HRF index is a little, you maybe could see some structure, but so it's a little hard to tell from this view. Here's the mean volume. By the way, this is a high-res data set. This is 0.8 millimeter isotropic fMRI. And here's the on-off model. So these colors clearly aren't as bright as these, likely due to the very high spatial resolution of this data set. But it's still indicative of good signals, and we can maybe compare the goodness of fit or the variance explained by this very simple first on-off model against the fractional value that happens later in the algorithm. Obviously, there's a pretty good relationship between the two, which is a good sign. They are not identical, of course, and that is expected. Okay, so those are some of the basic figures. Let me go back to the figure directory and look at some of the other ones. Some of the less important figures. So this is a plot of the cross-validation performance for the GLM denoise step of the algorithm, trying to increment the number of nuisance regressors per run that we add. By default, that evaluates up to 10, and in this data set, there was some boost going to 1, and the chosen number of nuisance regressors shown in red. Now, the y-axis is very strange, so let's not try to interpret the units, and really we're just looking at the pattern here. So just for other examples of that plot, this data set, seemingly lesser of an importance of adding these nuisance regressors, and that's okay. And the last one, let's look over here. Whoops. This data set, this session seemed to benefit substantially more, if you visually at least, looking at this trend. And it did choose many more, 6 nuisance regressors per run were chosen. Anyway, variance across data sessions is in fact expected, so these all look fine. Another figure, somewhat less, not terribly important, PC voxels. So this was actually used for the cross-validation choice in GLM denoise. Basically the median of all of the selected voxels here, as indicated by white, were used to inform the y-axis here. This figure is not that critical. It's just a way to summarize the overall performance across the voxels. Other figures, again, not terribly important. This is a simple depiction of an automatic threshold. That's fine based on the histogram of the on-off r². So this is really just to figure out a single number, in this case, roughly 0.4, that's used to essentially threshold the on-off r², and that's used for the GLM denoise step. But again, if there's something wacky or off in the data set, this might be a helpful diagnostic to determine what's going on. Okay, let's move on. This is an interesting figure. As the axes show, it's a plot of all the voxels in the data set. Their r² achieved under the on-off model, so something like this. And the y-axis is the href index that's ultimately chosen for that voxel. Now, there's a little bit of noise added to the y-axis in order to actually see anything, because the y-axis is discrete. These are indices, one-based indices from 1 through 20, corresponding to the library of hrefs. And just to kind of depict that, we will talk about this figure in a minute, but there's a library of href, or 1 to 20 ranges from blue to red here, from a very fast href to a very slow href. Anyway, so a little bit of jitter is added to the y-axis just so we can see. And what we're looking for here is, in some sense, sanity of the href selection. Let me pull up a few of these just to give us some diversity. Here's a different data set, and another one. And in fact, I should probably arrange these in a interpretable fashion. Let me actually close this. So let's look at this figure, but also compare against the two things being compared, which is the quick and dirty assessment of where signals are, the on-off r², and the href index. So as we saw earlier, it's a little tricky to see the relationship because there's very few voxels that have any signal, according to this view. But if you look at this scatter plot, I mean, it's essentially these voxels, which are very small. This was deliberate because some data sets may have many voxels. But if you look carefully, there are voxels that achieve very high r² corresponding to these regions here. And the href index selected for these are roughly in this range, between 9 and 16. All right, for comparison, let's do this for example 2. So we have the on-off r². We have the href index. Here we already noticed by eye the signal, the href index was structured, and here's the quantitative plot. And then finally, we have the on-off r², the selected href index, and the scatter plot. So comparing these, many differences. The ranges of values for the x-axis are quite different. They're very strong here and moderately strong here. You can see the vertical direction is kind of different. So the range here was roughly, 9 to 17 or roughly so, and then here it's roughly 8 to 17, so pretty comparable. But this data set seems to be later, where most voxels that have good signals are delayed, 14 to 19 roughly. So this scatter plot gives you a better sense of what's going on in terms of the href index. And that nicely leads us to yet another plot, which is very informative, this one. So let me bring this up, and this is a somewhat new addition to GLMsingle. Oh, that goes with this one and this one. All right, so let me explain what this plot is. So overall, the goal of this plot is to do diagnostics. This is fitting different flavors of models to the data. These models don't actually change the final answer that GLMsingle provides, but the goal is it can actually reveal things you didn't know about your data set, which might allow you to go back and fix your use of GLMsingle. And we'll actually see an example of that in a minute. All right, so let me walk through what these figures are showing. What the code does, and actually it's prior to any of the actual GLMsingle algorithm, it fits a Runwise FIR model. So FIR standing for Finite Impulse Response Model. Now, in order to do this, it makes the simplifying assumption that all conditions that you specify give the same response. So this is in some sense the same assumption as the on-off model, and that reduces the number of parameters and actually makes it estimatable for some types of experiments. And just to give an example of that, so going back to the example we have loaded in, this is a 583 condition experiment, somewhat insane, but it works. And this is just what the design matrix looks like in the first run of 12. Now, this experiment is largely a single trial experiment. There are some repetitions across runs, which makes possible the whole cross-validation aspect of GLMsingle. Anyway, but I bring this up to give the idea that this on-off assumption is essentially collapsing across the columns. So if I just sum across the columns, we essentially have a one condition experiment. And we could fit this model under the idea that we expect in each voxel the exact same evoked response to every single trial. Now, of course, this isn't really true for most interesting experiments, but for the purposes of fitting this FIR model, we're going to make that assumption. Okay, so in this very first analysis, we take each run of data separately and just fit, well, we construct the single predictor on-off model, and then we expand that using finite impulse response basis functions. So you essentially have a different predictor for every time point in the response. And the default is to estimate this up to 30 seconds post trial onset. So we fit the FIR model, getting essentially an estimate of the time course for every voxel, but for a single condition, which is assumed to be the sum across all the conditions. And after we do that, we have to summarize, since we have many voxels, these time courses. So there's an automatic step where we take the R squared, so the variance explained by this very special model, this Runwise FIR model. We actually have an R squared for all 12 runs. So I'll just quickly show you what that looks like. So here's run 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. As you can see, it's kind of noisy and kind of weak, but it's still valid. And I'm showing you the last one here, which is the run average. So I literally average the values in these 12 plots, these 12 runs together. So now you can start to see clearly the signal voxels that we've already seen earlier. Okay, so anyway, I'm showing this because there's an automatic thresholding step based on the distribution of values in this plot. The top 1% of voxels are chosen as kind of a quick and dirty mask, and then we average the time courses observed for those voxels. And that's what we're seeing in this panel. Now, this mask is held constant across all of the runs, so we can directly compare what's going on, and we get an empirical estimate of the HRF, or the evoked, stimulus evoked, or condition evoked time course, averaged across all the voxels that we selected in each of the run independently. And this gives us a lot of information as to potential things going on in this data set. Finally, the red is simply the mean of all the runwise estimates that we see here, and that's plotted here. There's a horizontal line at 0 just to help our eyes out, and finally there's a dotted vertical line corresponding to the peak of the red averaged time course, and that's going to show up in this panel. This panel shows simply the bold amplitude estimate of each of these runwise time courses at that time point. So at time point roughly 7, here are the corresponding bold amplitudes observed for each of the runs, and there's a direct correspondence therefore between what you see on the left and what you see on the right. This makes it a lot easier to see what's going on. In particular, if you notice that one run is completely bad, in the sense that there's no evoked responses or it looks weird, this can give you some clue as to potentially excluding that run. Finally, at the bottom, we get a visual depiction of the href library that's used in GLMsingle. So the rainbow colors from 1 through 20, that's the default. This is the href library, which was convolved with the stimulus duration you provided to give these time courses, and we're visualizing that. Notice there's a one-to-one correspondence in the x-axis across this plot and this plot. So the library is shown in the rainbow colors, and we have the href assume thing showed in black. So this assume thing is used as a very initial step, for example, for the on-off model. And again, it's here to help us diagnose any potential strangenesses that might be going on. Okay, so given this plot, we can observe many things. this is critical because this gives us a deep look into the actual time courses going on in the data set. And it's critical because if you get the href wrong, and drastically wrong, you might completely corrupt the analysis. And so by looking at these plots and comparing it to the library that GLMsingle eventually uses, remember this is just a very preliminary diagnostic analysis, but as you can see, there's a very good correspondence here, and we can be pretty confident that the library is going to accurately match the time courses that are present in the data set. In fact, we can do that in this plot. So remember, this is the same data set, and we had noticed, at least by eye, that for the few voxels that carried signal, the algorithm was choosing between 9 and 17, let's say, href indices, and that would actually correspond to these colors here. So kind of a greenish to reddish color, which would be roughly peaks around here. And if you just eyeball that up here, it does seem sane, does seem correct that these href indices should be the ones selected for the voxels that carry signal, which is consistent with this look at the data, which again is our diagnostic FIR model. Okay, so now that we understand the nature of this plot, we can start to compare what happens in other data sets. So this was the data set with very strong signals. Notice the bold response is much stronger, 5% bold change compared to this first example. Also, the time courses are highly consistent across runs, which is a good sign. And that also shows up in the amplitude. So the peaks as determined at this time point, I guess that's 6 seconds after trial onset, which is the peak of the run average, which is shown in red, as we mentioned. Anyway, the amplitudes are highly consistent. So that's good. And we can also visually compare against the library. Notice the library looks a little different, and this is because the stimulus duration in this experiment was longer than the one in here. But we can now visually compare across these two plots, and it should be the case that it matches what we see here. Remember, the voxels that have good signals their href indices are indicated here. So similar to the first data set, roughly 8 to 17 or so, which are roughly these colors, greenish to reddish, which it's a little hard to see, but you can convince yourself that it is inferring a reasonable href library choice, given what we see from the diagnostic plot. And let's look at one last example. This is the third data set. Here we notice the href indices are quite delayed. In this data set, there's a few strange things happening. I guess you could poke and do some further digging to see what's responsible maybe for this very strange time course. So this would be the second run. So maybe something happened in that run, or there's an artifact or something happened. So that's not a good sign. But if you look at most of the runs are fairly consistent in the FIR time course estimated based on the data in individual runs. Now, if one was concerned about run 2, by the way, it does show up in this amplitude plot, which would be this dotted line, as you can see. It's exactly consistent. One easy potential solution is to simply exclude that run if you believe something strange is happening in that run. Now, looking at the time courses again, we can confirm that these time courses that are derived from the data itself are fairly late compared to the library, and that should correspond to indices roughly from 14 to 18, which would be more of a orange to dark red color. And again, if you zoom in carefully with your eyes, you can kind of confirm that this does seem sensible. Bear in mind that, again, this look at the data is critically dependent on the top 1% of the voxels, so it may or may not be completely accurately matched to what you see up here. Yeah, and again, it's the top 1% based on the FIR model R-squared, which for this data set, let's take a quick look. Here are the 9 runs and the average of those 9. And I will zoom in. Actually, no, let's do it like this. So here's run 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the average. So clearly the average doesn't look as good as the other data sets. However, we can convince ourselves there is structure. This doesn't mean anything is wrong other than signals are weak. However, we still can tell the difference between voxels responsive to the experiment and surrounding voxels, so that's good. The individual run R-squareds that we're seeing here, 1, 2, 3, 4, 5, 6, it does look quite noisy, and this is unfortunately expected given the fairly weak signals evoked in this experiment and the limited number of time points in each individual run. So we sort of have to look at these and do a assessment of how much we can infer. But if you look at these individual run estimates, 1, 2, 3, 4, 5, 6, 7, 8, you can sort of convince yourself that there's at least a signal in probably all the runs. So if you focus on this region here, oops, so run 1, run 2 is a little strange. Remember, that's the strange run. But 3, 4, 5, 6, 7, 8, 9. Again, you have to hedge this against the noise level. But anyway, by staring at this, you can make an expert assessment for yourself whether or not you believe there's a problem with the data. But if you, anyway, I will leave it at that. Anyway, but the point is that keep in mind that these FIR inspections are based on the top 1% of the run averaged R-squared. So it's basically the brightest 1% of the voxels in this data set based on this assessment are being summarized here. Okay, so again, just to pop up a level, the Runwise FIR model doesn't affect anything that GLMsingle does. It's done as a very initial step just to help you diagnose and see any strange things happening in your data set, specifically with regards to time courses. This can be quite useful for figuring out what's going on if you see outputs that don't look great. Let's see if there's any figures we haven't described here. I guess it's really just this last set. So after all is said and done and the GLMsingle algorithm is finished, we added these runwise depictions recently, but the main figure that sort of summarizes data quality is under the type D model, which is the last model, with that has the href selection, the GLM denoise use, and the ridge regression. So after all those components are in, what is the variance explained of the final model that GLMsingle ends up with? And obviously brighter is better, and it should look more or less consistent. It's not going to look identical to other looks of where a signal exists. For example, the on-off model. The on-off model obviously has weird assumptions, like all your conditions evoke the same response, but it's useful as a quick and dirty assessment. And clearly there's a very strong relationship between these two measures, and that's a good sign. We can do a quick look at how it looks in these other data sets. So here's the on-off model. Very good relationship. And in this data set, we have this. And this is the on-off, and this is the type D R-squared. So there's a high relationship, and that's good. Now, as I mentioned, it also computes this R-squared measured, but only using the data from specific runs, so one run at a time. And here's how that looks. Now, it's going to be noisier for sure, in the sense that the metric may have speckles, given the fewer number of data points going into the calculation. But what we're looking here for is stability, and potentially trying to find or see if any run is strange. Maybe the subject fell asleep or had too much head motion or something like that. And as I step through these 12 runs, you can see that it's fairly consistent, in fact, highly consistent across runs. We can compare visually to, say, the second example, where we do the same thing. Here we go, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So highly consistent. That's a good sign. And then let's just see how it looks on this last data set. Here's run 1, 2, 3, 4, 5, 6, 7. Now, of course, whether or not this is consistent across your runs depends on how you distributed your experimental conditions. So if you had a peculiar distribution, you might actually have very different evoked responses in different runs. So you want to be careful in how you interpret the stability or lack thereof. Let me show one example that is a little bit less stable, I think, maybe. Let's see. Maybe example 4. Yeah, let's look at, no, actually, let's look at example maybe 6. Here we go. So this is a completely new data set that we haven't stared at yet, but let me just zoom in on these figures. So in this data set, we have 4 runs. 1, 2, 3, 4. As you can see, the first run looks pretty good, and then runs 2 and 3 and 4 are somewhat weaker. Now again, you have to weigh this against, do we believe these? Are these noisy, given the few number of TRs that we have in each run? And you also have to weigh this against what actually happened in the experiment. Anyway, so that's one example of where there are fluctuations, and then I suppose it's up to you to decide what to do about it. And just for additional information, here's the corresponding Runwise FIR results. It is somewhat unstable, which mirrors presumably what we're seeing in this other look at the results. Okay, so that takes us through the figures. It takes a little while to get used to what we're staring at and to interpret any given session, but it's especially these figures, the FIR figures, are very useful if you notice any data set that doesn't look quite good. It can help you diagnose what's going on. And especially if you have many subjects or many sessions on the same experiment, it's very useful to do a direct comparison of how these figures look across those instances. Now let's turn to one specific example. Let's clear this. So there's one example data set I have here that actually doesn't look very good. In fact, it looks like something's completely wrong. And I think this is instructive as an example. So this is example 5 here. If I pull up frac value, I don't see anything but black, which highly suggests there's no signal that it detected. Href index is hard to look at, but it doesn't look very structured. Here's the mean volume, just for reference. Here's the on-off R squared for reference. Let's just look at the run average for the diagnostic model. Doesn't look good. And then, I don't know, let's look at this last one. Okay, so here's an example of a data set that I don't see any usable signals, and that's not a good sign. Now, this is where the FIR diagnostics come to save us, potentially. As you can see, these look very strange. There are a few runs that look extremely strange, 7 and 8. It's not clear why this is happening in this data set. Now, arguably, if you look carefully, the first few runs seem maybe okay. So dark blue seems to have a expected shape of an HRF. And if you look at the run average, if we just trust the data, it does end up with something that's kind of like an HRF, but notice it's very fast. Like the peak is very quick. It's 5 seconds or less than 5 seconds after trial onset. This is somewhat expected given the experiment was a very brief stimulus. And this was a subject in that experiment for which the HRF seems extremely fast. And we know that there is variability in the time course of the hemodynamic response across subjects, so maybe we got unlucky here in a sense. Now, if we look at the library, it sort of seems that the HRF library should have captured it, but clearly it had trouble doing that, and this is due to all sorts of reasons having to do with the exact trial timing and all that type of stuff. However, we've already figured out a solution, and I'm going to show you what that solution is. So recall this, we use the vanilla call with all the defaults to generate the various figure outputs that you saw here. And one solution for this strange session, to rescue it in a sense, is to make some decisions as to what's going on. So one decision is the signal strengths are very, very weak in this data set. So notice the bold response only peaks at about 1, and even for the best voxels. And so maybe we're just pushing the envelope when it comes to this session. And given that the canonical href, so that's actually something to stare at. So the black here is what the on-off model assumes. And the on-off R squared values are very bad. And if you visually compare this, notice if you compare, say, the general peak in the empirically observed time courses is roughly here, and you compare that to what the black time course is, in some sense, it kind of mismodels it completely. So the bulk of the black time course extends about there, and it essentially covers both some of the positive, but also some of this, it's already gone negative in the empirically observed time courses. So one hypothesis is that this mismodeling of the href as embodied by this black curve completely messed up the characterization of the data. Now, one strategy of GLMsingle, given that it is highly customizable, if you like, is basically to give up on trying to do the href library for this session. Maybe there's high levels of noise or low amounts of signal, or the subject's hrefs are variable or something that we don't fully understand. So one strategy that we've already done here is down here. We can go through it. So what happened was we already ran this session through the vanilla GLMsingle trial, estimate single trial, and one of the files that saved, this is somewhat of a new addition, is this file called Runwise FIR. And if you look at the documentation, it is documented what it contains. It basically contains the basis of this figure. So what we can do is load this, this file, and it contains essentially what's in this figure. And so what we want to do is basically fix the href to something empirically observed. So this red curve, and that's contained inside of this variable FIR grand average. So it has 21, it's a vector that's 21 long. The first time point is coincident with the trial onset, so that would be time 0, and it persists at the TR of this data set. So in this example, then, we're going to recall it again, but we're going to use some of the options. We're going to turn off this whole library estimation. We're not going to bother with doing this, and we're just going to fix the assumed href to be the first 9 time points in the grand average FIR, as we just saw. So that would be from here, and then we can count 1, 2, 3, 4, 5, 6, 7, 8, 9. So I just decided that my prior, or my guess as to what the href is really just an href that looks like that for the first 9 time points. Well, I forgot where it landed, like that. So I'm going to extract those time points. So again, this would be 8 TRs after trial onset. So that would be 8 times a TR of whatever the TR was. Okay, so we're going to give that as a vector, a column vector, to this new call, the GLM estimate single trial. And that's it. And then we're going to rerun and save the outputs to a new folder called fix. So in the fix case, let's move some of these windows aside. We can pull up some comparisons. So that's on off R squared. This is the, well, this actually should look the same. Remember, this is a diagnostic model that makes no assumptions about the href, and it's the same. And then we're going to look at type dr squared just for a visual comparison. So clearly something helped, right? We get these nice punctate regions. By the way, this experiment is expected to only drive very little bits of cortex, so this also fits other expectations. So in some sense, we've rescued this data set. Just to show you some of these figures, this is the frac value for this new call. As you can see, there's some hotspots basically corresponding to this. That's good. href index is all blue just because we said turn off the library, so it effectively just uses a library of 1 href, so everything is index of 1. Some other figures that might be of interest. So let's look at the Runwise type D. So below is using the entire data set, and here is using just the time points from individual runs, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So if you scroll through these, it actually looks fairly stable. So it would seem to imply that the subject in the experiment was consistent. The subject stayed awake, did whatever the experiment was, fairly consistently across the 13 runs. And it does therefore imply that what happened in this initial call was due to estimation trickinesses and the, for example, inappropriateness of the canonical href that we used in, say, the on-off model. Like this analysis just failed simply for getting the href wrong. Now, there are many other approaches you could use. You could tailor the library, only use the first several, and you can do that by appropriate use of the flags that you call GLMestimate trial with. Here we just did a sort of a brute force, crude approach where we just turn off the library and just use a single href, namely this red time course here. Now, it turns out it was peculiar. These results are peculiar to this subject. Other subjects ran on this exact same experiment did produce figures that showed very strong, very good signals. Okay. So that was a lot. I think we're done. We've looked at figures and didn't really talk about what GLMsingle does, of course, because we assume that you're familiar with GLMsingle. And hopefully looking at these figure outputs will be very informative for just making sure that your data are fundamentally sound and potentially catching problems and suggesting ways you could recover or fix data sets. And we just saw an example of that for this example data set, number 5. I should just mention while we're at it, the function documentation includes descriptions of all the figures that we sort of just went over, as well as the specific variables saved in some of the files that you get out. For example, these files are the somewhat potentially very large files that contain the single trial betas. But we recently added, as we just saw, this file which contains some of these diagnostic results. And there's also a file called design info. I guess we can take a look at that, which contain some basic statistics on your design matrix, essentially, or that's the primary thing it has. These numbers are produced by the GLMestimate trial as very fast. So once you call it, it starts reporting some basic experimental design statistics to the command window output. So you can kind of read through that and make sure that it is consistent with what you expect in the way that you designed your experiment. Okay. That's about it, and hopefully you found this helpful.